Hello, welcome to this video. Today I just want to briefly explain some trends in reactivity. It's a it's a question I got. So how do you explain trends in reactivity in the periodic table? So this is one periodic table. Okay, I got it from nih.gov. I'll put this in the description. So some of the common trends are that as you go down the series for alkali metals or alkali earth metals for that matter, you get more and more reactive. Okay, more and more reactive. Okay, conversely, as you go down the halogen series, or the oxygen group, they call it chalcogens, but the halogen series, right? Go down the halogen series, they get less and less reactive, which is, why is this trend here? It seems very strange that your left side and your right side may have opposite trends. And what's more is that, for example, in displacement reactions, fluorine will displace chlorine, bromine can displace iodine. Okay, these two you don't really see much because they are radioactive. They don't exist in nature. You have to make them artificially. But why is this the case? Whereas for, let's say, a metal, maybe calcium can displace magnesium, something like that. Why are these things happening? And even among the transition metals here, like iron, chromium, magnesium, vanadium, some of these displacement reactions happen as well. Let's say copper is so-called, in a sense, less reactive, whereas copper metals are less reactive than, let's say, manganese or iron. Okay, there are reasons for that, but the core concept of chemistry is that everything has to do with electrons. Okay, everything has to do with electrons. Okay, so I'll draw the nucleus here. Okay, I'll draw the nucleus here. All right. So this nucleus, remember, it's a positive charge, very tiny, very tiny. Remember, it's being surrounded by electrons. So let's say if this was helium, right? Okay, maybe I'll use a different color, yellow color, maybe. Okay, I'll take this color, yellow. I'll draw a very crude looking electron. So remember, like the first shell, if you know your shells, your first shell is kind of having 2 electrons. Your second shell has, if it's full, it has 8. So I will just draw around the nucleus thing so that it doesn't like intersect the nucleus and makes it look a bit ugly. So if it's like a full ring, you'll have maybe 8. Okay, 8 electrons. Alright, and remember the objective of the so-called having a stable shell configuration is to get a full shell, or something that resembles a full shell. So remember, we will talk your standard chlorine, or maybe fluorine. Okay, I don't want to draw so many electrons. Chlorine is like that. Okay, so you have 1 in your outermost shell, you'll have something like this. Okay, 7. Fluorine also, you'll have 7 in your outermost shell. It just needs 1 more to finish up. Okay, but why is fluorine and chlorine, while they have the same number of outermost shell electrons, why are their reactivities so different? Okay, so let's take a closer look at the fluorine shell. The fluorine atom, the fluorine atom has 2 electrons in the innermost shell, followed by 7. Okay, I'm just going to put the F there where the nucleus normally is. Okay, the F will be where the nucleus normally is. Alright, so it will have 7 outermost electrons. Okay, chlorine has 17 proton, right? So I'll need to have 2, 8, and 7. So that's 17. So let me draw 2, 8, and 7. Okay, let me use blue color. Okay, even though that's not the traditional color for chlorine, but okay, I will draw again. write Cl where the nucleus is. Remember, in the center of the atom, the nucleus is where the positive charge lies, a very big positive charge in fact. Okay, so I go 1, 2, 3, 4, 5, 6, 7, 8. Alright, so this is a chlorine, the two innermost shells. So one more, you will have the outermost shells. Okay, and by outermost shell, it really means that it's physically further from the nucleus, right? Okay, so alright, then let me draw an electron now. Okay, so this electron can come from sodium, it can come from some other metal, right? Okay, so if an electron comes in and these two guys say, hey, I want an electron, who will get it first? Okay, who's more strongly like competitive in terms of getting the electron? Okay, both of them want one more electron, right? Okay, so which is the one that so-called has more positive charge, so to speak? Because everything with electrostatics, electrons and protons, opposites attract. Okay, you have a plus charge and a minus charge, opposites attract, right? That's how electrostatics work. So opposites repel and like charges repel, opposites attract. Okay, so when the electron comes and looks at this fluorine, okay, fluorine has this positive in the center, very positive. It has a few negative charges here in the innermost shell. So it has 2 electrons worth of negative charges in the innermost shell. Alright, so when it comes here, okay, if it comes here, it would see like, okay, I have a positive charge that wants to keep me around, but I have a negative charge that wants to kick me out, right? But overall, this positive charge is stronger than the negative charge, so I'm kind of staying. Alright? With chlorine, it's a very similar story. You have an electron, if it comes in here, okay, this chlorine will have a positive charge. This is a positive charge. Alright, how many negative charges are in there? So you have one shell inside of negative charge, another shell of negative charge inside. So this one has, okay, maybe there are more protons here, right? There are more protons here, but there are also more electrons inside. Okay, so we have more protons in the nucleus, but we also have more electrons. So it's a bit difficult still to compare. Then what then is this deciding factor? Okay, I want you to notice how far the electron is from the center. Okay, because this is the negative charge, this is a positive charge. Now, if you have a standard positive charge and a negative charge, let's say these two are maybe 2 meters away, and then the other one, very extreme example, is 2 cm away. Okay, which of these has the stronger attraction force? Okay, so if you know, I mean, just by intuition, like when you bring a charged object near your hair, you have to bring it close for it to get some effect. Like if you have your head and then you have a charged hair, and then you bring a balloon or some plastic object, and this happens to be charged. Okay, your hair will only like stand up next to the balloon when you bring the balloon close enough. So actually your charge, so to speak, the effect of opposites attracting or negative repelling, this electrostatic attraction and repulsion will weaken with distance. Okay, will weaken with distance. In fact, it will weaken with the square of distance. Okay, it's proportional to 1 over r squared, where r is like distance or radius or whatever. Okay, so if you look at the chlorine atom, this chlorine atom has a bigger r than this fluorine atom, right? It's a bigger R. So, okay, fluorine and chlorine, both of them have like positive and negative charges inside, so it's a bit hard to compare, because even though chlorine has a more positive charge in the center, in the nucleus, it also has more negative charge. So it's very hard to compare just like that. However, one of the easiest ways to see is to look at the distance of this electron from the center. Is the electron closer to the center for this fluorine or for this chlorine? So remember I said if the positive charge and the negative charge are closer to each other, they tend to stick more. Okay, so for this case, fluorine, the nucleus is actually closer to the outermost electron. Okay, the extra electron that comes in. So actually the negative charge is closer to the positive charge. All right, it is like one shell away, rather than over here it is two shells away. So if you think about it, the electron here is more attracted to this fluorine than it is to this chlorine. Okay, so if these two atoms are, say, competing for one electron, the fluorine will grab it away. So it's like an arm wrestling match, right? So fluorine has a stronger attraction for electrons, so it will like arm wrestle electrons away. In fact, it is sometimes so strong that if there's an electron here, okay, so let me erase. Now roughly you know what this is. This picture is going. Let's say you have a fluorine atom here, and it's happily going by. So this is the outermost shell. I'm not going to draw everything inside. And this is a chlorine. And then let's say this chlorine has a full shell here. Okay, what will the fluorine do? The fluorine is so reactive, and it wants that extra electron more than this chlorine. So what will it do? It will arm wrestle this extra electron to come over here. Okay, it can be any one of these electrons for that matter. So if you have Cl minus plus a fluorine, the likely case is that the fluorine will arm wrestle this electron away from the chlorine ion. So this is in effect how displacement sort of works. Is one way of thinking of displacement. It is with this effect. So what are the proper names for the effects I just described? Okay, the proper name, okay, of how attracted this electron is, okay, to the fluorine atom is called electronegativity. Okay, electronegativity. Alright, so the fluorine here is superbly electronegative as compared to the chlorine. Why? Because remember the charge, the outermost electron, the last electron, is actually closer to the nucleus than chlorine. So we call this, chlorine has an extra shell of electrons inside. Remember what I was telling you about? Chlorine has an extra shell of electrons inside compared to the outermost shell. Alright, so there's extra distance between the outermost shell or the outermost electron and the nucleus. Okay, what is this effect called? We call this the shielding effect. Okay, how do I spell shield? Shield. I can't remember my spelling. Yep, this is shield, yes. Shielding effect. Okay, so why is this called shielding effect? Because you can think about it like this what do you call it? This middle extra shell of electrons, they act as a shield. They act as a shield to so-called protect the outermost electron from the influence of the nucleus, right? From the influence of the nucleus. Okay, so yeah, if you, let's say you go to, for example, bromine, okay, if you go, for example, to bromine, you will have yet another set of electrons to shield, again, to shield the outermost electrons from the nucleus. So that is what basically shielding effect is. And you go to iodine, you add another bunch of electrons, and the distance between the nucleus and the outermost electrons is even further. So that's why you can see that there's a trend here from fluorine going all the way to iodine. It is because of this electronegativity effect I was talking about. So if you look for electronegativity on Google, you will find some things here on, for example, science notes, blah blah blah. You'll notice that the most electronegative elements are red color, while the least electronegative elements are what do you call that? Green colored. So actually, the halogens are more electronegative than most of the other elements. So electronegativity is one explanation for this reactivity. It's how badly the atom wants to take an electron in to form an ion. That's what electronegativity is about. It's a very long word, but that's what it's describing. But can this explain the alkali metals? Okay, alkali metals have a very different trend. Okay, alkali metals. So you have lithium. Okay, you have lithium. Okay, again, it's the same effect, positive and negative charges. Okay, it will have one outermost electron. And let's say sodium. Okay, sodium will have 2 inside, 8 over here. 1, 2, 3, 4, 5, 6, 7, 8. And 1 outermost electron. Okay, so again the same rules apply, right? It's the same rules apply. Okay, the same rules apply. If the distance is further from the nucleus, if the distance of this last electron here is further from the nucleus, okay, there is more shielding effect. Okay, there is more shielding effect for sodium. There's more shielding effect for sodium than for lithium, for example. Right? So, but conversely, this is producing the opposite effect here. Sodium is supposed to be more reactive than lithium. Why? Because again, remember, this is an electron, negative charge. This is a positive charge. Alright? So the more shielding it is, the more shielding effect we have between the nucleus and this electron, the more distance we have, and the easier it is to lose electrons. Alright, easier it is to lose electrons. So we call this effect electropositivity. It's just like the opposite way of electronegativity, because electropositivity is just how badly you want to lose your electrons. Alright, so this is some of the terms we use. Of course, if you want to keep using the electronegativity nomenclature, the way of naming things, nomenclature. Okay, electronegativity. Alright, you want to keep using the electronegativity nomenclature, sure. That means lithium is more electronegative than sodium. But in this case, with lower electronegativity, with lower electronegativity, you will have even what do you call that? You have more reactivity. Why? Because it's easier to lose the outermost electron due to this shielding effect that you see here. Okay, most if not all of chemistry has a lot to do with this, how these electrons behave. Okay, it's just the positive and negative charges and how they interact with each other. This law of attraction and repulsion is what actually determines how the whole periodic table behaves, pretty much. Okay, there are some other laws the what do you call that? The shell structure you see here, it is not determined by the Coulomb's law. Okay, the law of attraction and repulsion of like and opposite charges. Okay, or opposite and like charges. Okay, all this shell structure here is kind of determined by quantum physics. Okay, but I don't want to go there. Just assume that this shell structure is there. Okay, someone solve the equations for you and you get this shell structure. Okay, but the consequence of these two laws actually give you most, if not all, of how the periodic table behaves. It is all explained due to the movement of electrons from atom to atom, or ion to ion, or whatever molecule to whatever molecule, and so on and so forth. So hopefully this, okay, time's up. I don't take too long, but yeah, hopefully this explains why there are trends in this periodic table. So this is the electronegativity table. Again, I will show in the description. You can go and check it out yourself. See what are some of the interesting trends here. This one really helps to help you visualize. And then this one is what do you call that? Yeah, this just a normal periodic table, nothing too special. But from here, you should be able to see some trends. All right. Right. So yeah, that's all I have for you. Thanks for watching. Hopefully this is going to help in your chemistry exams, or help you understand what's going on behind the scenes as to why some of these elements behave the way they do. Okay, thanks a lot. I'll see you again.